and welcome to this video in which we will be performing calculations of the type you would see on a heating curve or a cooling curve. Now, there's going to be two types of processes here. One in which there's a change in kinetic energy and hence an increase or decrease in temperature. And the other in which there's a change in potential energy. So that would be our second type of calculation, and they need very slightly different formulas for those. The first is when we're looking at a temperature change of a particular phase. So this is not a phase change, this is a phase, this is like, let me see if I can do it this way. This is like heating a solid. So increasing the temperature of a solid or increasing the temperature of a liquid. So we're going to maintain the same phase, but we're going to look at changes within that phase. So we've got enthalpy or Q, because almost always at this level, we're going to be doing things at constant pressure, so we can equate those. And I like to call this the MCAT formula, and just a way to remember it. So that heat, and that's going to be in joules, is equal to the mass in grams times a constant, I'll talk about that in a second, times the temperature change. Now that can be in Kelvin or Celsius because the temperature change is the same, whether you measure it in Kelvin or Celsius. So that part doesn't matter there. Let's look at this constant. It's called the specific heat capacity. Capacity is an ability to. And so in this case, it's the ability to suck in or release heat without changing temperature. So things with a high heat capacity, high heat, you can add a lot of heat and you'll have smaller temperature changes, a smaller change in temperature. So if I'm comparing two substances and those two substances have the same mass and I add the same amount of heat, the one with the larger heat capacity will have the smaller change in temperature. Hopefully that clarifies that. So its official definition is the amount of heat required to raise 1 gram of a substance 1 degree Celsius. So that's why you see it as joules. Let me rewrite this in a bigger way here. It's the joules required for every 1 gram to change 1 degree Celsius. And we'll often put a dot, a big dot there, or sometimes a dash to show you those are both in the denominator there. Okay, so that's the formula we're going to use when we're increasing the temperature of a given phase of matter. Now, what are we going to do though when there are phase changes? If you watched my previous video, you know that during a phase change, there are no temperature changes. So if there's no temperature change, that would be 0, and that would imply no heat's involved, but we know that's not true. So we have to use a different constant in this case. And we're going to use, oh, that should have been fixed. Sorry, I must have fixed it before that. That should say delta H of fusion, not just H of fusion. So my enthalpy involved in melting, for example, would equal the mass or grams that I'm going to use times the measured amount of joules for every given gram. And so grams cancel and I'm left with joules. Now be careful, sometimes you'll see these constants given in kilojoules. Now later on in the year, you'll see a unit, or at a different time, at least for my honors kids, we'll look at the mole. And sometimes it's given, instead of joules per gram, joules per mole. So just hold that thought for now, that there are other units that we will be dealing with. If you remember our SI unit for amount was this weird unit called a mole. And we'll look at that later. Okay, so delta H of fusion, also called the enthalpy of fusion, okay, is the amount of energy required to change 1 mole or 1 gram of a substance at the melting point. Now be careful. In the previous math, our change in temperature will provide the sign. Here, we have to provide the signs. Okay, so if we're looking at melting, delta H of fusion would be a positive value. Remember, if you put it on the stove, will it help? And the answer is yes, so it's endothermic. But if we were looking at freezing, we would use the same value provided, but we would have to change its sign. It would still be the same delta H of fusion, but now it would be a negative to reflect the exothermic process. Vaporization is very, very similar. This is the energy that is required to vaporize as a positive value or condense as a negative value are 1 gram or 1 mole of the substance. So enthalpy of vaporization. Okay. All right. So let's take a look. You've got to be very careful and sketch out your processes or list your givens. So I'm going to use my guess method. So I'm going to do my givens, and I'm given 346 grams of water, and I'm given an enthalpy, so that's my mass. I'm given an enthalpy of 2.26 kilojoules for every 1 gram. So if you put that as a firm unit or as an equality, you see that's a conversion factor. So now all I have to do, you can do unit analysis, dimensional analysis, or memorize a formula that's mass times the delta H of vaporization. So it's 346 times my 2.26 kilojoules per gram, and this was grams. So my grams would cancel. And if I did my math right, 782 kilojoules of energy required to vaporize 346 grams. Now let's take a look at this one. I have a mass equal to 1.044 kilograms. I have an initial temperature equal to 98.6 degrees Celsius, and I have a final temperature equal to 32.3 degrees Celsius. Now, my formula is MCAT, so Q is equal to my mass times my heat capacity times my delta T. So those are our givens. You and guesses check your units, and you'll notice here I have grams in my heat capacity, but kilograms here. So I need to convert my kilograms to grams. So there's 1 kilogram for every 1 times 10 to the 3rd grams. So that's 1044 grams. Celsius is fine as long as it's a delta. So my delta T is always final. So this is my final minus initial. 32.3 minus 98.6. And my delta T is minus 66.3 degrees Celsius. Notice that this formula actually, if you always do your final minus initial properly, your sign of Q is going to emerge from the mathematics. So Q is 1044 grams times my heat capacity, 4.184, times my change in temperature. And degrees Celsius will cancel degrees Celsius. So this is grams. This is joules per gram degrees Celsius. And this is degrees Celsius. So I just want to show you grams cancels grams, degrees Celsius cancels degrees Celsius, and my answer will be in joules. Okay, and if I do that calculation, when I did that, I got, for this problem, minus 2.90 times 10 to the 5th joules. Had to have 3 sig figs because that temperature change had 3 sig figs. Now, think about whether it's logical. I have an exothermic process. Well, it's going down in temperature. Okay, if I cool something, I'm pulling heat out of it that's being released. So it's losing that heat. It's an exothermic process. Okay, so now this time I'm given my mass equal to 95.4 grams. I have an initial temperature of 25 degrees Celsius. And I have a final temperature of 48 degrees Celsius. They give me my heat this time. Q is equal to 849 joules. So the question is, what is my heat capacity? So same formula, I have a change in temperature. If there's a delta T, use MCAT. And all I need to do first before I can plug into MCAT is I want to check my units. I need grams, degrees Celsius, and I need joules because heat capacities are given in joules and grams. And again, Kelvin or Celsius works in this singular case. So I'm going to use my MCAT formula. So 849 is going to equal my mass in grams times my heat capacity, which is unknown. Okay, so times X times my change in temperature, which is always final, minus initial. That will give me 3 sig figs there, 3 and 3. So my final answer, X, or my heat capacity, is 0.387. And I had joules. I divided it by grams, and I divided it by degrees Celsius. Right? These are multiplied here, so my opposite operation will be division. So I had joules, I divided it by grams in degrees Celsius, and that would be my heat capacity. So hope that helped you wrap your mind mathematically around what happens when we add and remove heat from substances. Thanks for joining me. Good luck with chemistry.